Alright, so today we're going to be doing 512, which is going to be roots and zeros. So a lot of what we're doing today is putting a name and a concept behind things you already know in this course. So the fundamental theorem of algebra states that every degree n polynomial has n complex roots. The degrees tell how many solutions there are. These complex roots can be real roots only, imaginary roots only, or a combination of both real and imaginary roots. The degree of a two-degree polynomial has 2 complex roots, and a degree 3 polynomial has 3 complex roots. So this is things that you already know in this class, because you know how the degree always is equal to the number of roots? Yeah. We're just putting a name to that, and that's based on the fundamental theorem of algebra that allows us to make that assumption. So if we find or are given one complex root, either imaginary or irrational, then we can state that it is complex. Its complex conjugate is also a root. So it's always a little obscure to see it with A's and B's, so I want to show you like a real life example of this. So if they ever tell you, that like the square root of 2 is a root, then that means that negative square root of 2 is also a root. If they ever tell you that I is a root, then negative I is also a root. If they tell you that I plus 5 is a root, then I minus 5 is a root. And if they ever tell you something like 5 minus the square root of 3 is a root, then 5 plus the square root of 3 is the root. These are what we call conjugates, okay? So sometimes they're going to lack to give you that information, and you have to assume it based on the conjugate root theorem, okay? So I will literally say, based on the conjugate root theorem, you should be able to find an additional root for this particular polynomial. Now, you do not have to write these down, but you can if you want to. It is up to you. Any questions about that? All right. So now we're going to talk about some polynomial characteristics, which we've been doing in this class quite a bit, but we're going to add a few additional learning concepts in here as we do it. So of course we know that multiplicity tells us how many times a 0 occurs, and it affects how it looks on the graph, right? So a multiplicity of 2 gives us that bounce quadratic appearance, multiplicity of 1 gives us that linear appearance, and a multiplicity of 3 gives us that S-shaped type wave appearance, okay? So it says here, analyze the graph to the right. As you analyze, label the graph with characteristics in bold. So first thing I always do is actually identify the number of turning points, which is how many? 3. Remember, turning points are just changes where we go from increase, decrease, or decrease, increase. Now, the degree of the polynomial is always 1 more than the number of turning points, which means that it is 4th degree. Now, we learned about in 5.1, we learned that there are names for different degrees of polynomials, okay? So anybody remember what we call a 4th degree polynomial?
Quartic.
Good, quartic. And you don't have to have those memorized, as they are listed out in a chart in the front of your notes. But you can if you want to. If anything is beyond 5th degree, we just call it like 6th degree, 7th degree, because there are no names past that point. So from here, we're going to talk about the leading coefficient. So the leading coefficient sign is determined by what the graph's doing at the end of its lifespan. It's going up, so my leading coefficient is positive. Just a reminder to everyone. Alright, so now we're going to talk about end behavior. So end behavior is going to be based on what the graph is doing on both endpoints, okay? So what is the graph doing at the end of its lifespan? Good. It's going upward on both sides. Alright. And now we're going to talk about the zeros. So the zeros are where we cross the x-axis, right? So what are some values that we cross the x-axis here? Or touch the x-axis? Good. -4, 0. -2, 0. And very good. 3, 0. Now, what is the graph doing at -4? Is it crossing or is it bouncing? Crossing. And is it crossing in a linear appearance or a cubic appearance?
Linear.
So the multiplicity is 1. and the behavior is crosses. Now for the next one here, the multiplicity of the next one, it goes through in a linear appearance. So multiplicity is 1, and it also crosses. And next, right here, this bounces. Multiplicity is 2 when it bounces. And instead of crosses, we're going to say that it bounces. So now that we've done that, we can actually use all of the information that we've just come up with to come up with the equation. Okay, so you always do f of x equals. Now you can imply the equation based on the zeros. So see how we found 3 unique zeros? So that's going to yield us 3 binomials, individual binomials. So what binomial would give me the solution of x equals negative 4?
X plus 4.
X plus 4. What binomial would yield me the solution negative 2?
X plus 2.
Good. And what binomial would yield me the solution 3?
X minus 3.
Good. So you just go backwards, flip the signs, put them in binomial. Everybody is capable of doing this in this room, so please make sure you know how to do it. And multiplicity tells us what the power on each of those binomials are. So this one just has a power of 1, we don't have to write it. Power of 1, we don't have to write it. What do I have to put on this one here? Squared. That indicates that that 0 occurs twice. So pretty straightforward, pretty easy. Everybody in here can do that for sure, right? So now we're going to look at the y-intercept, which is where we cross the y-axis. 0, 3. And now relative maxes and mins. So these are the mins. The max. Okay. All right. So relative max occurs at 0, 3. Relative minimums occur at negative 3, negative 1. It's a little past negative 1. It's more like negative 1.5 technically. And 3, 0. Do we have an absolute? Yes.
This is kind of a little bit unrelated, but it's not a quadratic, or sorry, it's not a polynomial if it crosses the y-intercept more than once, right?
Good question. It's actually not a function at all if it would cross the y-axis more than once. So no, it wouldn't be a polynomial function because it wouldn't pass the vertical line test.
Right.
So for any reference, all functions always have only one y-intercept.
Okay.
Good question. So what do we know about the absolute maximum? Does this have an absolute maximum?
3.
Positive infinity.
Yeah. It technically doesn't have one. We would say that it goes off to positive infinity. So absolute means that we have a finite end. So we don't really have a finite end. We just have positive infinity. Now your absolute minimum will be a selection of one of your relative minimums. Which one is lower?
Negative 3, 1.5.
Good. Negative 3, negative 1.5. Make sense? Okay. We're going to do one more. So the easiest place to start is how many turning points we have. Good. Something I want to mention, it does come up on your homework. If you have a cubic degree term, like a cubic, if you have a cubic 0, like where it has that cubic shape, that counts as 2 turning points when you have that like this shape. So I just want to let you know that that counts as 2 because they're a little bit hard to see. But here we have very easily, you can see we have 4, which means the degree of the polynomial is
5.
Which is quintic. Very good. Okay. So, end behavior, this one starts down and ends up, which means that the leading coefficient is positive.
Positive.
It's always how it ends that determines that leading coefficient. It's positive, right?
I thought the leading coefficient.
You know, it's like the first one you.
They really did just leave us like that. Come on.
Well, leading coefficient refers to the coefficient in the equation. So I can see how it would be misleading. No pun intended on that. Just the word. But no, it's based on the graph itself. So if you are forgetting about end behavior, there is the chart on your 5.2 notes about it. So always use that as a reference if you need to. So now we're going to go ahead and find the zeros. We have one at -5, 0. Where else?
-1, 0.
Good.
3, 0.
Good. At the -5, 0, what's the multiplicity?
2.
Good, and it
Balance.
bounces. What about at the -1?
Also 2.
Also bounces. Good. Bless you.
That's good.
And what about at the 3, 0?
1, and then crosses.
Crosses. So there's two types of ways you can cross. You can either do it at a multiplicity of 3 or a multiplicity of 1. Multiplicity of 3 has a different look though, so you can identify it based on its appearance. Now we're going to write it in factored form. F of x is equal to. Now what you do is you write out as many binomials as you have individual zeros. And then you work backwards. So you set something equal to 0 that would yield you -5, and that would be
X plus 5.
x plus 5. So he's going to flip x plus 1 and x
Minus 3.
minus 3. Are any of these squared or to the third power?
X plus 5 and X plus 1.
Good, those two are squared. So the exponent on all of these are based on the multiplicity. You see that? So if this were like a cubic, it would have a third degree on it. Okay. What's the y-intercept here?
0, -3.
0, -3. And then we have our relatives, so our maxes and our mins. Looks like -5, 0, -1, 0, and then my mins -3, -4, and what else?
2 and -18.
Good, 2, -18. So another thing to notice, whenever you have zeros that bounce, they will either be a relative max or a relative min. Do we have any absolutes here?
Nope.
No, because my graph's going up forever and down forever. Good? Okay. So another thing I want to mention is the leading coefficient real quick. You see how this one's positive? That should be synonymous with the graph, the equation of the graph as well. See how right here the leading coefficient is just technically an implied 1 right here? What sign would this 1 have to be had this been determined to be negative?
Negative.
Good. So if you end up with something that has a negative leading coefficient based on the appearance of the graph, you need to throw a -1 or a negative sign in front of your whole equation. That's the only difference that you have to worry about in terms of the graph based on that information. Make sense? Alright, it's time to do a sketch. Usually you like these. Alright, yeah, I think so. So, the degree of this polynomial is based on the number of zeros. How many times does this 0 occur? Once. We have x equal, technically that's x equals -2. Then we have x equals 1, which occurs how many times? Twice. And then we have x equals 3. So the number of zeros determines the degree, and there are 4 zeros, so we have 4th degree polynomial, right? Everyone see how I got that? Based on the number of zeros. And 4 is an even or an odd number?
Even.
So we can tell that the degree is even. Why would that be important to us?
Because it determines the direction of the fish.
Very good. So this is an even degree. And is there a negative sign in front of this right here?
No.
No, so this is positive, even positive. Even positive is up and up on both sides. And I also would accept if you wanted to write positive infinity there as well. That's fine. Yes.
How do you tell if it's even?
If it's even?
Yeah.
So do you understand why it's fourth degree?
Yeah.
4 is an even number, that's all. Does that make sense?
Yeah, I think that's a lot
It's all like
to look at.
I know it's so obvious that it's just like overlooked, yeah. So well I kind of bless you, already did that step. So is everyone making the connection between the x-intercepts and the graph, equation of the graph? Now if you have a x-intercept that occurs twice, you don't need to list it out twice, okay? So here's how you find the y-intercept. I think Brant was asking this earlier. So you're gonna plug in 0 for x. That's how you find the y-intercept. So all I did was I replaced all the x's with 0. So what's 0 plus 2?
2.
What's 0 minus 1? Negative 1 squared? 1. And then this becomes, so we have 2 times 1 times negative 3, which is? Negative 6. There we go. So to find the y-intercept, you replace all of the x's with 0. Now we're going to graph our y-intercept as well as our 3 distinct zeros. And then we're going to do a sketch. So I know that my graph needs to end upward on both sides, so you have to be strategic about your sketch. And like I said, sketches are not meant to be as accurate as like a Desmos graph, it's just a sketch. So it can sometimes take you 2 or 3 tries to get it right, and that's okay. You're not going to be a sketch master of graphs overnight, okay? So it needs to start up, and it needs to touch my y-intercept. And then what does it have to do here at the 1? Bounce. Very good. So that's something of what your sketch can look like. Now, had they been more specific, and they said we have a minimum, an absolute minimum at 2, negative 14, we would have had to drop our graph down further. But since they don't specify any of that, we don't have to make our graph appear that way. Everyone feel good about sketching? Okay. So now we're going to talk about complex conjugate root theorem or theorem. I'm going to give you an early break present and make you only do factored form. Bless you. It is about 10 times easier. And on the homework, you only have to do factored form as well. So let's talk about this. This right here is an imaginary or an irrational root, right? That's the two you want to look for. You have to come up with its conjugate. What is the conjugate of this? You change the sign between the terms. Negative 1 minus 2i is its conjugate. That's how you find one's conjugate. You just flip the sign between the two terms if it has more than one term. So here's how you do it. F of x equals, you just do x minus the first given root, x minus the one we just came up with. Remember to put it in parentheses because we got the distributive property and all that. And then what's going to happen if I do x minus negative 1? It's going to become, when we subtract a negative, so here's my hint. If we yield a 0 of negative 1, what was the binomial that went with that? X plus 1. You see now? So with these two, I don't need you to distribute this all out. It's going to get really messy if you try to do that. So I'm just going to tell you what standard form would have required you to do. Standard form would have required you to FOIL this, so you have a binomial within a binomial. So that would have been about 8 arrows of multiplication. Once you were done with that, you'd then have to multiply by another binomial. So that's about 12 different types of multiplication you're doing. So this is a lot easier. But if you're feeling ambitious and you like algebra, go for it. And if you want to check your work with me, I'm happy to do it. So, next one we're given, you want to look for either a square root or an imaginary number. Do we have either of those things here?
Square 2.
Square root. What's the conjugate of that? Yeah, negative root 2. So how we're going to do it is, it's just going to be x minus root 2, x plus root 2, and x minus 1. And that's all equal to f of x. And you could have had the f of x in the beginning as well. That's fine. And that's all I'm requesting for today. And on the homework, that's all I'm looking for as well. So before you start the homework, I just want to mention